We're at the Penn State University main campus here. And here we grow silicon carbide crystals. And we can basically do end-to-end wafer processing here. So we can take them by actually growing them from the boule, then we can grind them into ingots, and then we can slice them into wafers from there.
So silicon and silicon carbide are both semiconductors. So they're both light switches, if you will, or for electricity. They turn it on and off.
Silicon carbide is different because we can use it with very high currents or high voltages, or use it at high temperatures, and it will still function.
The atoms hold themselves together much, much stronger than silicon. And that means then that they're able to handle a lot more energy than what silicon is able to do. And when I say energy, I mean more electricity, more voltage. So for instance, if you want to supercharge your EV and do it really quickly, like Tesla or other electric companies or electric EV companies, in order for you to go to that supercharger, you need to be able to get the energy from the charger to your car, right? So silicon carbide does that much more efficiently than silicon because it can manage the electricity much, much better than what silicon can.
Silicon carbide is still a crystal, just like silicon, but instead of having silicon at sort of every single position within the crystal, just think like a brick wall, right? There's an organized position for every single atom. In silicon carbide, there's different arrangements of silicon and carbide being stacked along the wall, or in this case, a wall in 3D.
The reason I brought this was so that I could demonstrate to you what the crystal structure of a couple of different polymorphs of silicon carbide looks like. So this model currently is configured in what we call the 6H polymorph. And if you look down through here, you can easily see straight through. And you can also see that the shape is that of a hexagon. It has 6 sides. We can very easily convert to the cubic model of this crystal if we break just a couple of these bonds. And now you can see that you can no longer look straight through that like we could in the 6H configuration. The reason this is important is because different polymorphs of silicon carbide behave in different ways. Their material properties are changed depending upon which form of the material you've made.
So we're really focused on improving the crystal quality, the wafer quality, with everything that we're doing here. We've got 4 or 5 different projects right now solely focused around how to make a better crystal. And it's not just about that individual crystal that's sitting in front of you, but it's about everything that holds it and everything that where you pack it in and all of the material that you go in to grow it in we call it source material or precursor material.
No, it's really very much like you cook up a recipe and you hope it's going to work. It's really like, not only silicon carbides, there are all sort of additives, a sniff of this, a sniff of that you throw into the pot and you hope it improves stuff.
We want to stay focused on industry relevant research. The R&D where we're developing, materials and information for PhDs also is going to directly impact the bottom dollar for companies.
I'm a postdoc researcher that's a part of the center. Specifically, I'm working on looking at different source materials, so different sizes of the starting silicon carbide material that will eventually grow the boules.
What we're doing is a lot of real hands-on work that people, even with a 2-year college degree or even certificates, can go in and make a difference in these systems, because you have to know about pumps, you have to know about mechanical engineering or running these different tools to be able to do that all the way up to a PhD level. So the range of people that can ultimately work in this area can be from mechanics all the way up to someone that's got their PhD in many years experience.
Not only do you need people who are working on the fundamentals, the building blocks, the atoms, the molecules, the crystal structure, you also have to need people that are able to run these things.
I like my job because I am learning new things all the time. There's a lot of innovation in this field, so you can't stay still. You have to keep learning.